Today, we're diving into the world of Sci-Compiler, an ingenious tool that's revolutionizing the way we create, manage, and deploy firmware for cutting-edge scientific research. Whether you're a physicist seeking to unravel the mysteries of the cosmos, a medical researcher on the cusp of a new discovery, or an engineer designing the next generation of detectors, Sci-Compiler is your gateway to turning complex hardware into a symphony of synchronized signals and data. In the last 60 years of physics experiments, traditional solution to implement trigger logic and readout systems involve the usage of several function-specific modules connected each other with cables. The system function is indeed defined by the kind of module used for coincidence, delay, digitizer, oscilloscope, TIDC, and the way they are interconnected. The large number of cables and the vendor-specific module configuration make quite complex the debug and maintaining of complex system with a large number of channels. Within an FPGA device, any bespoke logic or processing algorithm can be materialized by coding it in a specialized programming language. Traditional setups, crammed with hundreds of logic modules, multi-channel analyzers, and digitizers, can now be elegantly consolidated into a single board. This board utilizes ADCs to digitize analog signals, manages discriminated signals through digital input-output, and employs an FPGA to execute logic functions and manage data readout with precision and efficiency. Design firmware for FPGAs demands proficiency in specialized programming languages such as VHDL or Verilog, coupled with an in-depth understanding of the electronic circuits that materialize when the FPGA compiler transforms the human-designed firmware into a machine-configurable file known as a bitstream. Typically, users articulate their desired logic functions or algorithms through code. However, the compiler's output more closely resembles an intricate electronic circuit rather than traditional software. This complexity significantly steepens the learning curve for those looking to harness the full potential of FPGA devices. CAEN and Nuclear Instruments have pioneered a transformative solution that accelerates the transition from traditional electronics to FPGA-based readout and processing systems. Together, we've unveiled a new generation of digitizers featuring open FPGAs. These digitizers are designed with the end user in mind, offering the flexibility to reconfigure firmware with ease through our groundbreaking Sci-Compiler software, which utilizes intuitive visual programming. Users can concentrate solely on crafting their unique algorithms via a block diagram interface, while Sci-Compiler seamlessly translates this design into a functional bitstream, effectively bridging the gap between concept and execution. Sci-Compiler is very different from other visual programming software such as LabVIEW. LabVIEW typically generates software that runs on the PC in which the DAQ is inserted, processing data in near real time. The DAQ is limited to digitizing the data, while it is the acquisition PC's CPU that processes them. Sci-Compiler generates firmware that directly processes the data within the DAQ in strict real time. This means that it can fully exploit the parallelism of the FPGA, with a computing capacity much higher than that of the PC, and have delays in producing the processing result on the scale of nanoseconds rather than milliseconds, as happens with software running on a PC. Sci-Compiler is integrated with a vast library of virtual instrument IPs, streamlining the firmware development process. Users design their firmware visually with a block diagram, which Sci-Compiler then expertly converts into VHDL code. It proceeds to compile the project utilizing industry-standard tools from Xilinx or Intel and seamlessly downloads the compiled firmware directly to the FPGA. Sci-Compiler is a versatile tool designed to enhance scientific research and data analysis. Let's delve into some practical examples of what SciCompiler can do for us. Imagine performing pulse height analysis, PHA, with unparalleled precision. SciCompiler integrates a trapezoidal filter, charge integration, and peak detection. Not only that, but it also allows the incorporation of user custom algorithms, offering flexibility to meet specific experimental needs. In the realm of trigger logic, complexity is a common hurdle. SciCompiler elegantly converts intricate trigger circuits into a single board, diagram-based design. This simplifies the setup without compromising the sophistication of your logic systems. Now consider the real-time calculation of pulse shape discrimination. SciCompiler does this using multiple algorithms that analyze both exponential tails, commonly used with scintillators, and rise time, essential for helium-3 detectors. Moving forward, the reconstruction of interaction points in position-sensitive detectors is another task SciCompiler manages effortlessly. This capability is vital for enhancing the accuracy of spatial measurements in detectors, a cornerstone in many fields of research like neutron physics. Moreover, SciCompiler can execute real-time fast Fourier transform calculations with no dead time. This feature is crucial for implementing sophisticated triggers in data acquisition systems based on frequency detection. SciCompiler brings to the table high-resolution time-of-flight spectroscopy and multi-channel time-to-digital conversion, advancing the frontiers of temporal resolution in experiments. Customization is key in data processing, and SciCompiler stands out by enabling the implementation of any custom filter. It allows for the digital conversion of analog filters and the utilization of advanced fixed and floating point math operations, opening doors to unprecedented data analysis techniques. For analog signal generation, SciCompiler harnesses direct digital synthesis, Q/did-I-C algorithms, or lookup table-based methods, providing a wide range of options for precise waveform creation. Lastly, the real-time calculation of signal statistical parameters like average and sigma offers immediate insights into the data's underlying statistical behaviors. SciCompiler comes equipped with an extensive suite of IPs that facilitate a wide array of functions, from digital logic and mathematical operations to sophisticated algorithms. These include charge integration, trapezoidal filtering, peak detection, analog shaping, time-to-digital conversion, and center of mass calculations. Additionally, specialized IPs are readily available for tasks such as waveform digitization, data readout, and system configuration. SciCompiler boasts a user-friendly graphical interface that enables users to effortlessly select virtual instruments from an extensive catalog, and then place and interconnect them within a block diagram workspace. Comprehensive online support is readily available, offering detailed guidance for all the IP blocks. In this demonstration, we capture and digitize the analog signal emanating from a scintillator-coupled photomultiplier 2 (PMT). This signal is then processed through a pulse height analysis (PHA) chain that is based on a trapezoidal filter. The purpose of this sophisticated processing chain is to compute the energy spectrum in real time. The processing sequence consists of several key components: the trigger, the trapezoidal filter, the flat top sampler, and the histogram that calculate the spectrum inside the FPGA. Let's clarify the division of the firmware in each open hardware card. The firmware is partitioned into two primary components: the framework and the processing logic. The framework acts as the backbone of the card, expertly handling the ADC and D2A signal acquisition for both analog and digital inputs, memory management, and communication. It supports various communication protocols such as Ethernet, USB, or optical links, showcasing its versatile connectivity options. In essence, the framework is designed to manage the entire board seamlessly and transparently from the user's perspective. Users are not burdened with the intricacies of framework configuration. Instead, they can dedicate their focus entirely to the development of their unique processing algorithms within the processing logic component. This is where SciCompiler steps in. It intelligently molds the framework to conform to the user's block diagram design. By doing so, SciCompiler bridges the gap between complex hardware management and the user's need for a tailored processing logic. It ensures that the user's algorithm is perfectly integrated within the hardware, functioning optimally within the predefined system architecture. Each time a user places an object on the block diagram, be it a register, an oscilloscope, a list, or a spectrum, that has an endpoint capable of being read from or written to, SciCompiler takes a crucial step. It dynamically allocates an address space within the framework for this endpoint, effectively bridging the object to the internal local bus of the instrument. The software and readout libraries operating on the acquisition computer can then address each endpoint. This can be done using either the direct address or the name of the endpoint, allowing for the necessary operations to interact with the object. SciCompiler is a comprehensive suite composed of 3 interrelated tools, each serving a pivotal role in the workflow of firmware generation and data acquisition. First, we have the SciCompiler itself. This is the core engine where the design and generation of firmware take place, transforming your block diagrams into real, executable firmware for your hardware. Next in our toolkit is the Resource Explorer. Consider this the diagnostician of the suite. The Resource Explorer is instrumental during the debugging phase. Lastly, SciCompiler, which stands for SciCompiler Software Development Kit. This library is essential for data readout. Turning our attention to the Resource Explorer, this is a simply graphical software that serves as the window into the firmware's soul. With its intuitive graphical user interface, the Resource Explorer enumerates all the endpoints embedded within the firmware. The true power of the Resource Explorer lies in its ability to interact with these endpoints. Whether it's performing a readout of data or configuring settings, all of this can be done directly within the interface. And the most striking feature, all this functionality is at your fingertips without writing a single line of code. On new instruments, a web interface readout software is available. This interface allows to read out the date from the firmware directly from the instrument without using any external software. The web interface graphical layout automatically adapts itself to the firmware structure, creating a functional UI for the custom firmware. SciCompiler stands as the gateway for data acquisition from all compatible open hardware boards. This library is released to the open source community, as it is freely available on GitHub for anyone to use, modify, and distribute. It is cross-platform, with availability for both Windows and Linux systems. Runs even on Raspberry Pi. The library's versatility is highlighted by its compatibility with a plethora of programming languages and environments, including Python, C, C++, C#, VB.NET. LabVIEW, the library provides simple interface to access to any firmware element, like registers, oscilloscopes, and lists using a common interface for all SciCompiler supported board. SciCompiler supports hierarchical design, allowing complex systems to be built from modular blocks that can be nested and reused. This approach simplifies design, enhances efficiency, and improves maintainability by enabling independent development, testing, and updates at the module level. SciCompiler allows for easy multi-channel design using hierarchical structures to avoid duplicating diagrams. Designers can replicate subdesigns across channels and choose which interfaces to share or keep channel-specific, streamlining development and enhancing signal processing. Hierarchical approach affords the flexibility to configure channels independently, ensuring efficient design and tailored functionality. SciCompiler serves as both a firmware generation tool and a powerful simulation platform, offering time-efficient code simulation that accelerates the development cycle. Its rapid simulation aids in quicker debugging by providing detailed insights into nets and signals, leading to easier issue resolution. Additionally, it enhances test coverage by allowing users to simulate extreme cases, ensuring firmware robustness before deployment. Sci-Compiler features an advanced detector emulator capable of generating test stimuli to mimic the behavior of real detectors interfacing with firmware inputs. This allows the firmware's ADC input during simulations to be substituted with realistic data sources. Sci-Compiler offers remote compilation services on a dedicated CAEN server, eliminating the need for lengthy local compilation. Secure project transmission and seamless integration with the Sci-Compiler environment allow for easy offloading of resource-intensive tasks. After compilation, users are notified and can download the firmware directly within the interface for convenient device programming. Download Sci-Compiler now and start your free trial immediately. Experience for free all the functionalities of Sci-Compiler and begin creating your first design today.